session. So if you remember, last time we talked about mathematical induction, which is a very powerful technique for proving many statements. And this was the last example that we covered last time, if you remember this. Okay. However, sometimes in an induction proof, it is not very easy to show that Sk implies Sk plus 1. So that's why we need something a bit stronger. So let's talk about proofs by strong induction. Okay, so I'm gonna continue our discussion on induction by talking about strong induction. So that's, I think it's section 14.3 in the textbook. So this is about the strong induction. Strong induction. Okay, so like I said, sometimes in an induction proof, it is hard to show that statement Sk implies Sk plus 1. Okay, it's hard. It may be easier, so maybe it's easier, may be easier to show that some lower, you can say here some lower, let me adjust this tablet, some lower Sm with M strictly less than K implies Sk plus 1. Okay, could be easier. For such situation, for such situations, there is a slight variant of mathematical induction. Okay, so that slight variant is called strong induction. So let me tell you about the proof by strong induction. So this is the let's say the method of the strong induction. I'm gonna write here. Okay, so proof by strong induction. So let's see what this implies. Strong induction. You can ask me questions anytime. So the goal is to prove that a certain statement, let's denote it by Cn, is true for all n. One, for all n, right? Okay, the first, so here are the steps. So how do we prove that? So the proof consists of two steps, as in the standard induction. The basis step, so step 1, or the basis step, step 1, right, we need to prove the first few or several Sm as needed. This is, we will exemplify this as needed. And the inductive step, step 2, inductive step, step 2, right? Step 2. We need to prove, in this step, we need to prove that if S1, S2 up to Sk are true, then Sk plus 1 is true. So prove that S1 and, this is and, logical operator, S2 and so on, Sk, if these are all true, this implies Sk plus 1, true. Okay, so again, this symbol is the logical AND operator. Okay, all right. A simple example. You can ask me questions if you want. We can discuss these things all the time. Okay, a simple example, and very, very well known, is this one. It's also in your textbook. So let's prove that any postage of 8 cents or more is possible using 3 cents and 5 cents stamps. Good luck with that nowadays. I mean, probably you can't find such cheap stamps. Okay? Okay, so how do we prove this? Well, the first step, you know, we use the strong induction. The first step. Well, obviously the statement is true. Is true for postages of 8 cents, right? And 9 cents. Why do we need both? You'll see that immediately. Of course, we can say, you know, 8 is 5 plus 3, so obviously you need 2 stamps here, one of 5 cents, the other one of 3 cents. 9 is 3 times 3. Well, 3 plus 3 plus 3. So we can do that. So the basic step works. We need to verify the statement. So this is, let's say, S8, and this is S9, right? So this is true, and the other one is also true. Right? This is, and the proof is here in front of our eyes. Okay. Let's see, why do we need two verification in the basis step? Okay, so let's assume that or k is strictly greater than 10. Well, actually than 9, so greater than or equal to 10. Okay, and for each m between 8 and k, and for each a, assume a postage of m cents, right, can be obtained. Exactly with okay, so just let me scroll down. Okay, exactly with 3 cents and 5 cents stamps. Okay, so in other words, we assume this. We assume that S8 is our statement, you know, S8 meaning that a postage of 8 cents can be covered by stamps of 5 cents and 3 cents. We saw that 5 plus 3 is 8, right? And S9 and SK is true. This is what we assume. And the question is, does this imply SK plus 1 true? That's the question, right? Okay, well, it's easy to see that because, okay, so K plus 1 equals K minus 2 plus 3, right? It's true, right? Well, then we know that SK minus 2 is true. Then this implies SK plus 1 true. Why is that? You just add a stamp of 3 cents value, right? So you know that K minus 2 cents can be covered by stamps of 5 cents and 3 cents value, right? Then you just add this new stamp of 3 cents value, and you obtain that K plus 1 cents are covered, you know, this sum of K plus 1 cents is covered by stamps of 5 cents and 3 cents value. Does it make sense? Anybody? So do you understand the argument? Can anybody hear me?
Yeah, we can hear you.
All right. Okay. All right. Because I was thinking, oh, I'm alone. So the connection dropped. But I'm glad you are here. So is this argument clear? So once we can cover k minus 2 cents by stamps of 3 cents and 5 cents, then we can cover k plus 1 cents, by just adding one more stamp of 3 cents value. Makes sense, right? So the conclusion is that Sn for n greater than or equal 8 is true. Okay? Now, look what happened here. Why verifying for just 8 cents for a postage of for a postages of 8 cents is not enough? Because then if you assume, okay, this is the basis step, 8 equals 5 plus 3, that's fine. And you don't verify for 9 cents, right? For a postages of 9 cents. Then this argument here, as you can see, is based on sk minus 2. So when you try to prove, I mean, S8 doesn't imply S9 directly, right? So when you try to prove S9, in fact, you need, so for S9, you need needs what? Well, S what? Think about this. So for proving, you need S6, right? This is not a good thing, right? So you need to go over S9 as well. Even for S9, maybe we should have continued that. So for S, so okay, so we have S8 verified, S9 verified, S10. For S10, we need what? So this is kind of, we need S7. This is still not good. We haven't verified this one. So maybe here at this step, we should add S10 as well. That's easy, right? It's 5 plus 5. So S10 is true, right? So add this, S10, verify S10 in the basis step as well, because otherwise, when you start this in, the dominoes effect, for S10, you don't have S7. But from now on, S11 is doable because it implies S8. We already verified S8. So for S11 is based on S8, and we know that this one is true. Okay, so you understand the argument. Why we need to verify the first several Sn as needed. So for example, here in the first step, we need to verify 3 of these. Make sense? Make sense to you? Hopefully it does. And let's continue with this. Okay, now the next thing that we'll talk about is about proofs by smallest counterexample, which is a hybrid of induction and proof by contradiction. So let's talk about section 14.4. I can give you many examples. Actually, I hope we'll have time to go over those exercises and problems at the end of this chapter. Okay, so let's talk about section 114.4 now, which is about proofs by smallest. This is an M, right? Smallest counterexample. Okay, this is a hybrid.
Is that proof by small cost?
Smallest.
Okay.
Smallest. From small, right? Smallest counterexample. My handwriting, maybe, you know, which is a hybrid of induction and proof by contradiction. So this one is, it is a hybrid. You'll see that immediately, of induction, mathematical induction, and proof by contradiction. Contradiction. Okay. Well, here is an outline. So an outline of this method. Again, the goal. Let me just scroll down this. So here is the goal. The goal again is to prove that a certain statement, call it Sn, for n, let's say greater than equal 1, so for n equals 1, 2, 3, and so on, is okay. So is true for all n, right? This is the goal. Okay, the first step in order to prove this, step 1, is to check that the first statement S1 is true. So check that S1 is true. That's the first step. Okay, it's like, you know, in the regular induction, right? So so this is kind of the basis step in regular induction. Step 2. Okay, for step 2, we suppose that not every Sn is true. So this is arguing by contradiction. I can say here arguing by contradiction. Suppose not every Sn is true. Okay, step 3 then. We have an integer k, which is the smallest, for which sk is false then, right? Because, you know, Sn is not true for all values of n. So let k, which is greater than 1, obviously, we verify the statement for 1 in the first step, be the smallest integer with sk false. Okay, this comes from step 2. We know that the statement Sn is false for certain. This is our assumption for that the Sn is false for certain values of n. Step 4 and last consists, okay, of the following thing. We know that k is the smallest integer with sk false. So sk minus 1 has to be true. Is true. But this may imply that sk is true as well. And obviously this is a contradiction with step 3, right? We know that sk is false from step 3. This is in contradiction, you know, this should be, you know, swords, but they don't look like that. With step 3. So that is the basic idea, okay? Now, let's see one example. Right? And we employ exactly this. So let me keep these steps here so I can watch them. Oh, well, this doesn't look very simple. Okay, yeah. Example. This is an application. Okay, so you have other, I mean, I can cook up an example which is similar with the examples that you have in the textbook. So I can say, you know, if n belongs, this is belongs to the set of natural integers, meaning, you know, n equals 1, 2, 3, whatever, one of those positive integers, then 5 divides 7 to the n minus 2 to the n. So this is our statement. Okay? So let's prove this. So here is the proof. So let's prove this statement by smallest counterexample. So let's say we use proof by smallest, by our method, smallest counterexample. Okay, step 1. So let's follow these steps. The first step, well, if n equals 1, so S1, this is what the statement says for n equals 1. 5 divides 7 to the 1 minus 2 to the 1, but that's kind of obvious because this is 5. So this is true. Right? We are done with step 1. Okay, now, arguing by contradiction, so we are moving to step 2. Step 2, which you see above. Let's assume that the statement, so Sn, is not true So we assume that this is not true for certain values of n, so not true for all n. This is our assumption, which is wrong, but we have to prove it wrong, okay? Now, step 3, so we follow the general guidelines. Step 3. Let k, which is greater than 1, we already verified that S1 is is true, be the smallest integer, natural number, right? For which five doesn't divide 7 to the k minus 2 to the k. Okay? Okay. So then step 4. Let's see what happens. So we need to get a contradiction somehow. Okay, we know that sk minus 1 is true. So sk minus 1, because k is the smallest integer for which this property doesn't happen. But we know that sk minus 1 is true. We know that 5 divides 7 to the k minus 1.
Professor, for step 3, is that saying 5 is not divided by 7k minus 2k?
No, 5 doesn't divide.
Okay.
Right? I mean, it's not a divisor of 7 to the k minus 2 to the k. So this is the smallest one. Okay?
Mm-hmm.
Now we want to prove that, this is impossible. I mean, in step 4, we get a contradiction, and the contradiction comes from our assumption in step 2. So that meaning, our assumption is false, meaning that Sn is true for all n, which we want to prove, right? So we assume now, we know that this one is true because k is the smallest integer for which this property doesn't happen. Okay, but from here we can rewrite this thing as 7 to the k minus 1 minus 2 to the k minus 1 equals a multiple of 8, a multiple of 5, right? 5 times 8. Okay, let's see what this leads us to. Then, okay, we have 7 to the k. I can multiply by 7 this. 7 multiplied by 7. So I'm going to multiply this by 7. And look what I get. Minus 2 to the k minus 1 equals 7 times 5a. 7 times 5a. Well, this is 35. Okay, but on the left-hand side, you have 7 to the k. And now I can decompose. Okay, let me write one more line. Not this. 7 multiplied by 2 to the k minus 1. And this has to be equal to 35 times 8. Okay, now this is 7 to the k, nothing done here. But 7, I can decompose it as 5 plus 2. That's obvious, right? Multiply by 2 to the k minus 1. And this is 35, 8. Okay, then I have 7 to the k. Okay, here I can say minus 2 times 2 to the k minus 1 is 2 to the k. And I'm going to move the other term to the right-hand side. So this is 35a plus 5 times 2 to the k minus 1. We are very close to our contradiction, because look what happens. So we have 7 to the k minus 2 to the k. On the right-hand side, we can factor out 5. That's very easy to see, right? So this is 5 times 7a plus 2 to the k minus 1. Or in other words, 5 divides 7 to the k minus 2 to the k, which is a contradiction. I mean, look here. I mean, these two provide, the obvious contradiction. On one hand, 5 doesn't divide 7 to the k minus 2 to the k. On the other hand, it divides 7 to the k minus 2 to the k. Okay, because this one here, the statement here, this thing represents just SK true, right? Which is, we assume this is not. I mean, k was the smallest number for which we don't have this thing. So is this argument okay with you? So do you see?
So I'm trying to figure out. So the last part, you transition from 7k minus 2k equals 35a plus 5 2k minus 1. I was just wondering, how did you get that?
Okay, I foiled this term. So I foiled this term here. Just a second. I foiled. So what do you have here? You have 5 times 2 to the k minus 1. Maybe I should write it different in a different place. Let me just go.
So you're just multiplying this.
Yeah.
Inside, and then
yeah.
Okay.
And I foiled that term, and then I moved the term that contains 5 to the right hand side.
Okay.
Just algebra, right? Little algebra. It has a negative sign, so you have minus 5 times 2 to the k minus 1. When you scoop it over, you have plus 5 times 2 to the k minus 1. And the other one is 2 times 2 to the k minus 1 is 2 to the k. All right?
Yep.
Now, by using this method, you can prove lots of other things. Like, you have an example. I'm not going to go over that one because it will take too much time. Related to the fundamental theorem of arithmetic. Actually, you can prove the fundamental theorem of arithmetic, which says that any integer, positive integer, has a unique prime factorization. You can go over that by yourself. It's a very simple example of application. Well, it's not so simple, actually. It's a fundamental theorem of arithmetic, but you can prove it by using a combination of strong induction and this argument provided by the proof by smallest counterexample. Okay, let me now talk a little bit about Fibonacci numbers. These are very important. That's a very important sequence of numbers. So let's talk a little bit about this section 14.5. Okay, it's about Fibonacci numbers. Fibonacci was an Italian guy. He lived in what is now Italy in the 12th century, and he published a book, actually a very interesting book, called Liber Abaci. And in this book, we have this sequence of numbers, which is very famous. So the sequence starts with F1 equals 1, F2 equals 2. These are the first entries of this sequence. And then you have a recursive relation, namely fn plus 1 equals fn plus f sub n minus 1. Okay, and this holds for all n greater than or equal to. So this is for all n greater than or equal to. So let's compute a few. Oh, I'm sorry, this one is 1, 2. I just moved to. Okay, let me erase this. This is 1. So it starts with 1, 1. Okay, so let me go back to this. Okay, let's compute a few entries of this sequence. Okay, so F2, F3, actually, F3, we have F1 and F2. F3, and this is F2 according to this recursive formula, plus, so n is 2 in this case, right? Plus F1. So this gives 1 plus 1. This equals 2. Then F4, well, it's F3 plus F2. Okay, so I have F3 is 2, F2 is 1, so this is 3. And as you can see, the numbers will start growing. I mean, the entries will start growing rapidly. F5 is 3, F is F4 plus F3. So this is 3 plus 2 equals 5. Then F6 is F5 plus F4, and this is 8. Anyways, as you can see, the numbers start to grow, right? So F7, I'm not gonna. It's F6 plus F5, and this is just 8 plus 5 is 13. So the numbers start growing really fast after that. It's F7 plus F6. This is 13 plus 8 is 21, and so on. The next one is what? Is 34. The next one is 55. Then you have 89, 144. The sequence continues like this. Then 300. No, the next one is 233. 377. You see how fast these numbers grow now. What's here? It's 610, right? And so on, right? So this sequence goes to infinity, in fact, right? Okay, now let's prove one important identity related to these Fibonacci numbers, and by using induction. So let's say this is, I don't know, like a little theorem. Let's prove that fn plus 1 squared minus fn plus 1. It may look like a complicated relation, but it's not that complicated. It has implications, very interesting implications. I mean, this simple fact that you see here. Okay, so let's prove, this theorem. So this is true for all n, for all n, let's say greater than or equal 1. All right. Okay, so here is the proof. Well, we use induction, right? So by induction, the proof is by standard induction. Okay, the basis step is to verify that the statement, so this is our statement, this is S sub n. What you see here, this is our statement. So this is S sub n. So the first step is to prove that S1 is true. Okay, so what's S1? It's F1 plus 1, so F2 squared minus F2 times F1. So for n equals 1, right? Minus F1 squared. Okay, so let's see what this one is. F2 squared is 1 squared. We know that. F1 and F2 are 1. That's the value of F1 and F2. Minus 1 times 1 minus 1. Okay, so as we can see, this is 1 minus 2 is negative 1, which is also negative 1 to this power 1. So that meaning, this is true. We verified the basis step. We are done with the basis step. Now, step 2. We need to prove that if Sk is true, then this implies Sk plus 1. So Sk implies Sk plus 1. This is what we want to prove. Okay, so how do we prove that? Well, brute force. So Sk being true means that Fk plus 1 squared minus Fk plus 1 times Fk minus Fk squared is indeed negative 1 to the k. So we know that this is true. This is Sk. Now we want to prove Sk plus 1 true, knowing this. So what's Sk plus 1? Well, Sk plus 1, we can write it very easily. I mean, right now. So it's Fk plus 2. K is K plus 1 now. So I replace K by K plus 1 here. K plus 2 squared minus Fk plus 2 times Fk plus 1 minus Fk plus 1. So K becomes K plus 1 in the above line, okay, squared. Okay, now we said we use, the brute force. We know that Fk plus 2, it's Fk plus 1. This is the definition of the Fibonacci sequence. Fk plus 2 is Fk plus 1 plus Fk minus, okay, here, this is minus. And Fk plus 2, again, it's Fk plus 1 plus Fk multiplied by Fk plus 1. I'm not going to do anything to that. I need everything in terms of Fk plus 1, So here is Fk plus 1 minus Fk plus 1. So the only term that I substituted for is Fk plus 2 by using the definition of the Fibonacci sequence. Okay, so this equals, I'm going to move it here because otherwise it will be a bit too crowded. Let's expand this binomial. I mean, the binomial expansion of that is Fk plus 1 squared plus 2 times Fk plus 1 times Fk plus Fk squared. I'm done with the first term on the right-hand side here, this one. Minus, I'm going to FOIL the second term. So I get, Fk plus 1 squared, which is good. we have a cancellation. We'll have a cancellation immediately. Minus, minus fk times fk plus 1. That's fine. I mean, this times this. Minus fk, oops, we have another one here, squared. Okay, we have this cancellation. And what's left is just minus this term here, minus fk plus 1 squared. Now, look, these two terms are alike, so we can combine them, and I have here just plus k plus 1 times fk plus this leftover fk squared. It's just a calculation, right? Okay, so this equals, I can factor out negative 1, obviously, minus fk plus 1 squared minus fk plus 1 times fk minus fk squared. This is beautiful, right? Because you recognize that this one is just, you know, the thing that enters in the statement of sk. So this is the left-hand side here, right? So this is the left-hand side of this equality. Of course, we know that this thing here is negative 1 to the k. And so this equals negative 1 to the k, which is just negative 1 to the k plus 1, and we are done. So this implies sk plus 1 true. And right, so a round of applauses, because, you know, from the induction, so from steps 1 and 2, we know that Sn is true for all values of n, for all n, by induction, right? So this is a very, very interesting thing. Okay, questions about this? So we have this identity. Now, what do we do with it? I mean, something interesting happens from this identity that we just proved. So this is the identity that we proved. This one, Sn, this statement Sn. Now, let me rewrite it here. And then I'm gonna, so a consequence or a remark, or let's say a remark. So we have this relation true for all n, fn plus 1 squared minus fn plus 1 times fn minus fn squared equals negative 1 to the n. Okay, now if we divide both sides by fn squared, we end up with fn plus 1 over fn squared minus fn plus 1 n over fn minus 1 equals negative 1 to the n over fn squared. Okay, now something interesting happens here, because, you know, we know that as n goes to infinity, fn, let alone squared, goes to infinity, right? So this implies that fn grows really fast. Then it seems like fn plus 1, so this is capital Fn, fn plus 1 over fn converges to a certain value x, which is a root of this equation, x squared minus x minus 1 equals 0, right? So this approaches the root of this equation because the right-hand side goes to 0. So you have, so if we denote, this, I don't know, by something like, xn, that xn converges to a value x, which is a root of this equation. What are the roots of this equation? We can use the quadratic formula. And we have 1 plus minus square root of 5 over 2. Okay, so we have 1 minus square root of 5, which is a negative number. That can be because, this is always positive. So this is out. But the other one is in. So it seems like the Fibonacci sequence, I mean, the ratio of 2 consecutive terms of the Fibonacci sequence has this interesting property that it has a limit. Okay. Now, if you compute this value, if you use a calculator, I'm going to use mine now.
So why do we scratch off the 1 minus square root of 5 divided by 2?
Because this is negative. So 1 minus square root of 5 over 2 is less than 0. Can be, right? Because, these are all positive numbers.
Mm-hmm.
I mean, this here is strictly positive. Actually, it's greater than 1. All of them, right? Because fn plus 1 is greater than fn. Keep in mind that fn plus 1 is fn plus fn minus 1, which is greater than fn, right? So that's why we can discard, this value. So this is not a good value, right? Only this one. Now, the value of this is about 1 point, I can approximate it, 62, right? Of course, you can get more decimal places if you want. Okay, well, this number is called the golden ratio. And so this is the so-called golden ratio. And it was really, important to artists, architects, sculptors in the past. It is said that even the great pyramid of Egypt were designed in accordance with this number. Or, the Parthenon in Greece was also designed having in mind this number, or many pictures. So this is somehow, let's say, related to beauty, to aesthetics, to harmony. Okay, it's an interesting thing about the Fibonacci numbers. And also it says something that for large values of n, the Fibonacci sequence behaves like a geometric sequence, because you have kind of this. You have for large n, fn plus 1 is about this ratio, or the golden ratio, times fn. This is kind of like, what happens with geometric sequences, right? I don't know if we have, time. If you have the textbook, we can do one of these problems if you want, but probably not in the 3 minutes left. So probably I have to stop here. I'm sorry for that problem with the server. The whole Purdue system had this problem for a couple of minutes, but it happened at the very beginning of our class, so we lost a few minutes. Go over the problems, at the end of this chapter. There are so many interesting problems. The odd numbered problems have solutions. The even numbered don't. So ask questions about those. Okay. Try to understand the others, which are with solutions in the textbook. That's it for today. And if you have any questions or anything, please ask. Otherwise, I'll have to stop here. Okay, no questions? All right, then have a nice day, and maybe I'll see you again, okay? All right. See you all.
All right, Professor.
Bye.